Assalamualaikum warahmatullahi wabarakatuh. We meet again in this video. But this time around, we will be talking about topic 4.5, triple integrals. By the end of this video, you as a student should be able to sketch the solid and the region of integration, determine the limit of the triple integral, and evaluate the triple integral using rectangular coordinates. So if you have your module with you, turn to page 254. So basically in this page we discuss about the properties of triple integral, and we also have the Fubini's theorem for triple integral. I really hope you can spend some time to go through all the materials on page 254, because this somehow very basic for you to understand, and you can understand it through your own readings. So we will move to the next page, where we will be discussing about evaluating triple integrals over more general regions. So before this, when you try to solve double integrals over region R, you should be able to sketch region R in two-dimensional coordinate system, because the region R will help you to determine limits with respect to variable yz if we are talking about rectangular coordinates, or r theta if we are talking about double integrals in polar coordinates. But this time around, when we discuss about triple integral, we are going to sketch solid G in three-dimensional coordinate system. So this is the difference between double integral and triple integral. When you have double integral, you have to sketch region R in two-dimensional coordinate system. In triple integral, you have to sketch solid G in three-dimensional coordinate system. Again, the purpose of sketching solid G, the reason is this solid G will help you to determine limit with respect to variable z, limit with respect to variable y, and with respect to variable x. So let's take a look at this example 4.5.2.1. Okay, where the question asks you to determine or to evaluate the triple integral for function z with respect to v. Let G be the wedge in the first octant that is cut from the cylindrical solid x squared plus z squared less than or equal to 1 by the plane y is equal to 0 and y is equal to x. So you have to sketch all these surfaces in the same three-dimensional coordinate system. So let me demonstrate. Okay, so basically you have z, y, and x, which is you have a cylinder, circular cylinder, and this circular cylinder will be traced along variable y. Okay, please remember back what we have studied in topic 3 point, not 3.2, topic in chapter 1. So you will have a cylindrical, we call it as circular cylinder. Then okay, I'll show you one by one, and then we will try to sketch it on the same three-dimensional coordinate system. Then you also have a surface y is equal to x. So okay, you have this surface, and then you also have a plane at y is equal to 0. Okay, so right now I'm going to combine all these surfaces into one three-dimensional coordinate system, 3D coordinate system. I will have z, y, and x. Okay, you have to remember we are interested in sketching these surfaces in the first octant only. So when we restrict our circular cylinder in the first octant, we will have this type of shape. And then we will add another surface, which is a plane. This is y is equal to x. Meanwhile, this is x squared plus y, not y squared, z squared is equal to 1. Then we have another plane, y is equal to 0, or xz plane. Okay, so you have to make sure this solid G comprises of all the elements such as x squared plus z squared is equal to 1, xz plane or y is equal to 0, and plane y is equal to x. And then you will end up with this solid G. We call it as solid G. From this solid G, you are able to evaluate the triple integral. Okay, so right now, what should I do? Okay, what should I do with this question? I have to sketch it, or I have to set up my own triple integral, which is, okay, I'll leave some space over here, and I have z, dz, dy, dx. It's up to you to either have dz, dx, dy or dz, dy, dx. Okay, so in this case, based on this solid G, again I have to sketch an arrow along z direction parallel to z axis. I see that since it is also bounded by the first octant, therefore z should always start at z is equal to 0, and then it will touch the solid, and the solid is represented by this equation, x squared plus z squared equal to 1. Again, you have to be able to make sure you know how to make z as the subject of your equation. In this case, I will get 1 minus x squared, and 1 minus x squared will be the upper limit with respect to variable z. So what should I do if I try to determine limits with respect to variable y and x? So I should be able to map the solid G, which is in 3-dimensional coordinate system, onto xy plane in 2-dimensional coordinate system. So project solid G from 3D onto xy plane in 2D. So you will end up with this curve. Okay, if you look carefully, you will end up something like this. So this is your region R. So again, since we have decided to solve this problem by using dz, dy, dx, which is dy, dx type 1 integral, I need to sketch an arrow bottom up parallel to y axis. So according to my observation, this is actually y is equal to x. Y is equal to x is the equation of that straight line. Okay, and then I will get y equal to 0, and then it will end at y is equal to x. Therefore, x will be the upper limit with respect to variable y. So before this, I know that the radius of the circular cylinder is 1. So the value over here should be 1. So x will start from 0 and then it will end at x is equal to 1. So this is the triple integral setup for this kind of question. So I really hope you get the idea from this question. So let's try to solve this question together. So I will get z squared over 2 and then I will evaluate from z equal to 0 until 1 minus x squared. From here I will get 1 over 2 1 minus x squared, and then I will integrate from y equal to 0 until x with respect to y, and then I will get y minus y x squared. Then I'm going to evaluate from y is equal to 0 till x. Don't forget 1 over 2. From here I will get x minus x cubed minus 0. So from here I will get 1 over 2 integrate x minus x cubed with respect to x from x equal to 0 until 1. From here I will get x2 over 2 minus x4 over 4, 1 over 2, then evaluate from x equal to 0 until 1. So from here I will get 1 over 2, 1 over 2 minus 1 over 4. So my final answer will be 1 over 8. So it will be quite a tedious process, and right after this I don't think that I have more time to give the comprehensive solutions. So I really hope your cooperation to go through the process on your own. Before this, if we have single integral, we can always use it to determine the area under the curve. Meanwhile, for double integral, there are two applications for double integral, such as you can use double integral to determine the volume of the solid, and you can also use double integral to determine the area of the region R. Meanwhile, when we are talking about a triple integral, you can always use it to determine the volume of the solid G. So according to your module on page 256, basically to determine the volume of the solid G, you should assume your function fxyz is equal to 1. And then by using this formula, you are able to determine the volume of the solid G. So let's take a look at the first example. Example 4.5.3.1. Okay, from this question, the author asks you to determine the volume of the tetrahedron bounded by all coordinate planes, and at the same time x plus 2y plus z is equal to 2. Okay, so right now we would like to determine the volume of the tetrahedron. Okay, so right now x plus 2y plus z is equal to 2 xy plane, yz plane, and xz plane, or equivalent to z equal to 0, x equal to 0, y equal to 0. So right now you have to sketch solid G first. Sketch solid G based on the description given by the authors in the question. So I will have Z, Y, and X. Then I will have X plus 2Y plus Z is equal to 2. You can find all the intercepts. By letting YZ equal to 0, you will get X intercept. So X is equal to 2, 2Y is equal to 2, Y is equal to 1, and Z is equal to 2. So I will get this tetrahedron bounded by all coordinate planes. Okay, so right after this, I need to sketch the region R. The region R can be sketched by mapping your solid G from 3-dimensional coordinate system onto XY plane in 2-dimensional coordinate system. Then you will get Y versus X. When you have Y versus X, the value here is 1, the value is here 2. Then this is your region R. The solid G is used to determine the limit with respect to variable Z. Meanwhile, the region R can help you to determine limits with respect to variable X and Y. So right now, the best equation to represent this red line is by assuming Z equal to 0, you will get X plus 2Y equal to 2. Okay, so right now, on this solid G, I have to sketch an arrow parallel to Z axis, and then in this region R, maybe we try different solution than what we have on page 256. Maybe we will try to use type 2 integral. So I have to sketch an arrow, and this arrow should be parallel to x-axis. So right now, I try to set up my own triple integral. Volume of solid G is equal to the triple integral your function f x y z equal to 1, and then dz dx dy. So right now, okay, so right now your z equal to 0, and then it will touch the surface of your plane, which can be represented by that equation x plus 2y plus z equal to 0. By letting z as the subject of your equation, you will get the upper limit with respect to variable z, such as 2 minus x minus 2y. And then please take a look at this region R. So according to this arrow, it will touch the y-axis first, and y-axis can be represented by x equal to 0, and then it will touch the red curve. The red straight line is represented by the equation x plus 2y equal to 2. So you have to make sure x is the subject of your equation, then you will get 2 minus 2y. And then y, please look at along y-axis, y starting from 0 until 1. So by using this limit, you will get the same answer like what you have on page 256, such as 2/3. So I really hope you can spend some time on your own to go through the solution on your own, or else you will spend more time to watch the videos. Okay, let's move to the next question. Okay, this question asking you to determine the volume of the solid bounded by the surface y is equal to x squared, y plus z is equal to 9, and z is equal to 0. So right now, we are talking about example 4.5.3.2, and then what should I do with this question? If you cannot put it in one coordinate system. Maybe you can try to sketch it separately and then you combine them later. So let's imagine y is equal to x squared will give us what type of surface. So by right, I have z, y and x, and then I will have a parabolic cylinder, and this parabolic cylinder will be traced along z axis. Okay, wait for a while. Okay, we're talking about this parabolic cylinder. Then z, y, x. Okay, then you have a plane. Y plus z is equal to 9. Y is equal to 9. Z is equal to 9. So I will have this plane, and this plane will be traced along x-axis. Okay, and also you have to take into consideration z is equal to 0 or xy plane. So most probably your surface will lies at the first and second octant. And then this is my z, my y, and my x-axis. So right now you have okay, wait for a while. And then as if you cut your parabolic cylinder at with the plane y plus z is equal to 9. And then you will get something like this. Okay, so this is your solid G. Okay, so this is the arrow to determine the limits with respect to variable z. And then in order to determine limit with respect to variable y, project your surface or your solid from 3D onto xy plane in 2D. Okay, this is my y, this is my x. Okay, so I will end up with this plane such as y is equal to x squared. From here we know the value here is 9, therefore when y is equal to 9, x squared is equal to 9, x is equal to plus minus negative 3. So this one plus minus 3, negative 3, and here is 3. Then this is your region R. Okay, so right now we try to set up our own triple integral. Volume of the solid G equal to triple integral. So right now your function fx, y, z equal to 1, since we are talking about using triple integral to determine volume of the solid G. Then it comes as dz, dy, dx. So maybe on this region R, I have to sketch this arrow. Okay, so right now what should I do? According to this region, this solid G, it will touch the surface, and the surface is represented by that equation y plus z is equal to 9. Therefore, since we are talking about plane z is equal to 0, therefore z equal to 0 will be the lower limit. Meanwhile, 9 minus y will be the upper limit with respect to variable z. And then let's take a look at region R. According to this red arrow, it will touch the parabola, and the parabola is represented by that equation y is equal to x squared, and then it will touch the line y is equal to 9. So 9 will be the upper limit with respect to variable y, and then right after this we have to determine limit with respect to variable x. So according to this region R, x will start at x is equal to negative 3, and then it will stop at x is equal to 3. So if you spend some time to go through the solutions, you should get the same answer, which is volume of the solid G is equal to 648 divided by 5. So this will be the final answer for this question. I think that's it for triple integral.